Good morning, good afternoon, good evening, wherever you may be. Welcome to Good Measure. My name is David, and I'll be your host today. Today we have Jonathan Cohen, VP of Engineering at NVIDIA. He's here today with us to talk about AI, NVIDIA, and so much more. Jonathan, thank you for being here. Do you mind quickly introducing yourself to those in the audience who may not be familiar with you or your work?
Yeah, happy to. Thanks for having me. I've been at NVIDIA a total of 11 years, about, with a little 3-year interlude. I went to Apple, and then I came back to NVIDIA. Before that, I worked in Hollywood in the feature film visual effects industry. So I've been in like the tech industry or the entertainment industry, I guess, for 20 years. My job now, so I lead conversational AI R&D for NVIDIA. And I guess we'll get into what that means, and I can say lots more about that.
Yeah. And yeah, so first off, I'd just love to ask you a few questions about how NVIDIA sort of utilizes AI, and just to quickly introduce it to my audience. And so I guess, like, how does NVIDIA utilize AI technologies, and why is it so important for a company that is very, for most people, very well known for GPUs to focus on this kind of technology?
Yeah, so at NVIDIA, I mean, we both use AI and we also power a lot of the other companies around the world that use AI. So maybe I can answer that question in two parts. So as a company, we think of ourselves as an accelerated computing platform company. So what does that mean? So take some problem that people want to solve with computers that takes a really long time. And if you could solve it faster, everyone would be very happy. It would be very valuable to the world. And so then we build a computing platform. By that, what I mean is hardware, software, APIs, programming languages, whatever that there's a whole stack of technology that then developers can use to solve their problems in that area. So for example, in gaming, that was really our first business. Video games are something people care about. You want them to run faster. They take a lot of computational power. And we built this accelerated computing platform for video games. We worked with Microsoft to develop DirectX API. We built the hardware. We lots and lots of technology in the driver. We worked with the game developers, game engines. So there's this whole stack of technology that makes games run faster. And so our business originally was focusing on that. But we always had this kind of broader vision that it's not just, we're not a video game company per se. We're an accelerated computing platform company, and video games were a really great business for us. And so now one of our largest businesses, and I guess it might be by now our largest business, close to it, is accelerated computing for AI. So a lot of modern AI is training very large neural networks or similar kinds of computational work. And that takes a lot of compute power. It takes very large computers running for a really long time. And people want that to go a lot faster. So if I'm going to train a model and it takes me a week, if I can train that same model in a day, that's a huge improvement to productivity and what companies are able to do. So the real product we develop, which we call NVIDIA AI, is this stack of hardware, software, interconnects, networking, system software, acceleration libraries like cuDNN, deep integration into software platforms like PyTorch, developed by Facebook, that are used for all of this. And so that's our main product. And that's very valuable to the world because the stuff is important and making it run faster is valuable. And so that's why, we care about it. And I can just briefly answer maybe a question from the other perspective. As an engineering company that builds technology, AI is tremendously useful to our internal work as well. So we use AI to develop chips. We use AI in quality assurance, visual inspection of dies. We use AI in some of the technology. So we have this technology, deep learning supersampling, DLSS, which makes games look higher resolution and crisper and better. That technology is based on neural networks. It was developed by people at NVIDIA. We train these special neural networks that can do this magical kind of upsampling, on big supercomputers. So AI is such a valuable technology that we couldn't develop and ship the products that we do and the technology that we build without AI ourselves. So we're both a builder of this platform, and then we use our own platform to build our platform itself. And so all of these things are really integral to what we do as a company.
Yeah. And so seeing as you brought up cuDNN, I'm just going to quickly jump into that. And so could you tell us
Sure.
a bit about NVIDIA and the deep neural learning network that you have developed, and like give us like a sort of simplified version of how the program utilizes GPUs to create a library for deep neural networks?
Yeah. So cuDNN initially was, I think, about 2013. So it's been around for a while now.
Mm-hmm.
The idea behind cuDNN was, if you look at the actual math involved in training a neural network. So when you train, well, originally it would be like AlexNet, which was one of the first popular computer vision networks, but any of these neural networks are that are used for all these different kinds of tasks today: speech recognition, image, object detection, autonomous driving, all this kind of stuff.
Mm-hmm.
The actual mathematical calculations that are involved, they actually boil down to a relatively small number of basic patterns.
Mm-hmm.
And so what we realized in cuDNN was, let's create a set of software routines, a very simple set of functions
Mm-hmm.
that are easy to use. So you just say, hey, I have this, in this case, it would be, I need to compute the derivative of a convolution.
Yeah.
I need to compute a convolution or the derivative of convolution. These are two basic calculations that you would do
Mm-hmm.
when you're training a neural network, whatever that is. Well defined. You can write out the equations. It's pretty simple to explain what the actual math is doing,
Mm-hmm.
but implementing it in a way that it runs really, really, really fast on our processor,
Mm-hmm.
because that turns out to be like the vast majority of the time you spend when you're training a neural
Yeah.
network and you're waiting for a week. Most of that time is in just a few of these mathematical operations.
Mm-hmm.
And so we created this set of optimized implementations of these mathematical operations, and we
Mm-hmm.
packaged it up and we called it cuDNN. And it was very popular, because what that means now is, when we make our hardware better, or we think of a new clever algorithm, or someone else even thinks of a new clever algorithm, we can take that idea, we can put it in our code, and you don't ever have to worry about it. So all you do, you're a user of TensorFlow or PyTorch, or
Mm-hmm.
you're someone who wants to train a neural network. You
Yeah.
just install cuDNN. You don't really care how it works, what it is, but you're guaranteed it's always going to give you the highest performance, all the latest tricks and little mathematical optimizations, or hardware optimizations, or whatever it is, and you
Yeah.
don't worry about it. You just get that for free. And you
Mm-hmm.
buy a new GPU. cuDNN just recognizes, oh, you have this GPU. It now allows you to do these special, secret optimizations under the hood, and everything you're doing just keeps running faster and faster. And that was when we first built cuDNN. The reason it was successful was because we demonstrated that. So there were other actual competitor software libraries at the time,
Yeah.
and what we kept showing is that maybe this month this other library is faster, but by next month we've caught up. And
Yeah.
then the next month there's something else that's faster. By the next month we've caught up. And we just kept doing that, release after release after release. Anything showed up was a little bit faster than us, but we caught up within a month or two.
Mm-hmm.
And so it's, I think the message to our users was, just adopt cuDNN and just program to our APIs and let us take care of the optimization. And we promise that over time you'll always have the best performance. And so I think that was a very effective strategy, and
Mm-hmm.
we've lived up to that for the 9 years it's still been in existence.
And so I guess speaking about just developing software and AI, what have been some of the benefits of developing AI at NVIDIA, and so like just doing it in-house, and how does it like help with the other products that NVIDIA puts out?
Do you mean, so are you asking for what are the benefits, like for me personally, to do this work at NVIDIA, or why does NVIDIA invest in this?
Like, why does NVIDIA invest in this?
Yeah, well, I mean, AI is the most transformative technology, I think, in my lifetime.
Mm-hmm.
I think what the lesson of AI, you could narrow it to neural networks, but I think more broadly,
Mm-hmm.
AI is that there are certain kinds of tasks, certain kinds of programs that we humans don't really know how to write, but we
Mm-hmm.
know how to create an algorithm, in this case, a neural network, that writes its own program. And essentially, when you're training a neural network, what it's really doing is it's learning an algorithm somehow.
Mm-hmm.
It's figuring out what calculation should the computer perform to detect your face in an image, or to recognize my speech as English, whatever
Yeah.
the task is. So
Mm-hmm.
I don't know how to write a program to convert audio signals into text, but a neural network does. And so that's an incredible leap where computers now can solve problems that we don't know how to solve ourselves. There's no human can do the things that neural networks can do. No human programmer can write a program to do the things that a neural network can do. And so because of that, we have across just a huge range of really important problems, the ability to achieve levels of accuracy and performance that just weren't possible before the rise of these deep neural networks. And so, I think every company today is either already using modern AI techniques or is figuring out how to do it because it's just so incredibly valuable. There's so many things that we want, like this conversation you and I are having, translating this into French, or if transcribing it, or removing the background from behind you so you can't see that I'm in a messy room. All of these things are using neural networks today. Playing a video game, I was saying before DLSS, and making the image look a little bit sharper. You have your iPhone and it recognizes your face and unlocks. All of this is using neural networks, and it's because they're just such powerful technology. So I think NVIDIA is like all companies in that we want to always adopt the best technology to solve the problems we care about, and that's just modern AI today.
And so speaking about like problems and language and conversation, I want to transition into something that you yourself are developing, and which would be just conversational and not AI. And so could you tell the audience a bit about Project Riva?
Yeah, so conversational AI broadly is at least the way we define it, is automated understanding of human language. So you and I are speaking in English. It's useful to have computer systems that can understand what we're saying, can respond, can understand the audio signal, can understand written communication. There's lots of ways humans communicate. And there's lots of things you can do when you can automate the understanding of that. You can build an application like Siri that you can have a conversation with. You can build in a call center. You call your pharmacy to order a refill, and if for something simple like that, instead of talking to a human, you can just do the whole thing through an automated system. There's no wait time. You don't have to wait on hold for 30 minutes to talk to someone. You just do it yourself. So many of these kinds of applications, or video conferencing. You speak French and I speak English, and we can still have a conversation because the system can translate between us. So that's just some of the use cases when you have systems that can understand human language. Riva is our platform for packaging up all these algorithms into a developer platform. So Riva provides routines for speech recognition, speech synthesis, some amount of language understanding. We will add lots more things like machine translation and the whole range of technologies all inside this platform called Riva. And so the point of Riva is that it's very customizable. It's developer friendly, so it's meant to be. Riva is not an application. It's again a platform for you to build applications with. It's very because it's NVIDIA. Everything we do is very high performance. You get the best performance. The fastest translation. You can handle the most simultaneous audio streams on a single machine. Riva is meant to run in the cloud or on-prem. It's meant to be, so it supports privacy in cases where I don't want all my, my users or my customers are talking, but I don't want to go send it to the cloud. I want to keep it in my secure data center. You can run Riva there. So it has these kind of features of like trying to be a platform that would be easy to customize and deploy and then integrate into really whatever application you want to enable with some kind of conversational intelligence.
And so I really just I'm personally really curious, and so like, are there some places that not many companies have looked for applications of this technology, but will actually benefit a lot from this technology? I'm really curious to know if you have any insights on that.
Well, I think there's lots of sort of obvious places where this is useful. Call centers is obviously useful. Video conferencing, like what you and I are doing right now, is useful. We've certainly come across some pretty interesting companies using Riva to do things that we didn't think of. Maybe one kind of example. There's a few examples that are in the realm more of like education. So there's a company called Tartil AI, which they make a Quran recitation tutorial program. So if you are Muslim and you're learning to recite, Quranic passages with the proper pronunciation in the proper, dialect of Arabic, which most people don't actually speak. It's using speech recognition. It will show you the passage. You say the passage, and it using speech recognition, it says, "Oh, you mispronounced this word here. You mispronounced this word here. Oh, this word should be pronounced like this." So it's a tutor. It's like sitting next to someone who is an expert in this language, teaching you how to speak these phrases, but fully automated as as an application. And I think that's like a really cool example of certainly something I never would have thought of building on top of Riva. And there's other things like applications that we've seen in like reading tutorial applications for kids. So kids can read a book and it reads the book and it shows you the text, and the kid can learn how to read, and the program tells you whether you read the lines correctly or not, these sorts of things, right? So I think education is like a very interesting area where conversational AI can make a big impact.
And I guess so, what are some of the most important things you've had to sort of consider when creating conversational AI? And what are some of the bumps along the way that you never really expected to encounter, but you've had to overcome while developing this kind of AI?
That's a good question. Well, I think one thing that makes, anytime you're working with language, excuse me, language is dynamic, it's constantly changing. Even things like it changes geographically. People speak English differently in different parts of the country. Obviously in different country, there's lots of countries where people speak English, but they speak English very differently. Over time, new words come up, new excuse me, new phrases, new proper nouns show up. Language isn't a static thing, it's a dynamic living thing. And so to build a conversational system that understands language the way people speak it right now, you actually need a system that's continuously learning and improving. And you need to be feeding it, lots of examples of, news broadcasts today, like right now, lots of cities in Ukraine, right? For example, people are speaking them all the time. And maybe 2 years ago, people weren't talking about, naming lots of cities in Ukraine, right? So even just the things that we're talking about are constantly shifting. And as a result, if you're building a conversational AI platform, it needs to be a dynamic thing that's constantly improving and shifting, learning new, slang, new lingo, new dialects, new place names, new people. What's a Dua Lipa? Well, now that's a name like people know. That wasn't a name anyone knew, a few years ago, right? So these kinds of things, I think, is one of the challenges in building a really production grade conversational AI system, is that it's not something you do once, it's something you do continuously. And then if you want to support many languages, you have to do this not in English, but now Italian and French and Mandarin, and and all of these languages are constantly evolving and changing, right? So I think that's one of the biggest challenges in building these kinds of platforms.
And so I guess speaking of building these technologies, and what have been like the biggest differences between working on this new R&D like project, if it's correct, with Riva, and in comparison to the QDNN project, and how has your management philosophy changed from project to project, and maybe even over time?
Well, that's a good question. I think they're very different kinds of technologies. I'm trying to think how to answer that in a succinct way. So I think QDNN in some ways has like a very well-defined metric. The QDNN is about train neural networks as fast as possible. And in some sense that's kind of easy to measure. Now it's not that easy to measure which neural networks. People today, there's technology called transformers, which is a very popular type of neural network. No one was doing that a couple of years ago. So we care a lot more about making transformers fast today than we did, like a few years ago. In the past, we cared a lot about 2D convolution, and that was all we did. And now, that's also important, but people do lots of other things. So the landscape of what you care about shifts, and so how you measure it shifts. But despite all that, it's relatively straightforward kind of thing. Conversational AI is different. It's harder to evaluate. For example, machine translation. So let's say I have an automated system that translates from English to French.
Yeah.
How do I measure how good it is? That's very subjective. You know, I have a sentence in English, and now I said my system has translated the sentence into French. Did it do it correctly?
Yeah.
Maybe the sentence in English is kind of funny, and the sentence in French loses the humor. Boy, that's a subtle question, right? Like these are really hard things to measure. So I think there's this added complexity with conversational AI in that because it's fundamentally like a human thing, it's harder to measure. And I think as a result, the way you manage a project, it's not as straightforward to manage it in terms of just like metrics. And you know, you can imagine if you're managing QDNN, you know, the master list is just here's our performance on a whole bunch of routines, and here's how fast we were, you know, last month, and here's how fast we were this month, and here's how fast we think we can be next month. And you're just sort of tracking all these numbers, and it's a very nice kind of quantitative engineering task. It's not easy. I'm not simplifying it. It's a tremendous amount of work. Very big team, very talented team working on that now. But it's a straightforward thing to think about. Conversational AI has this problem that I think it's a little more squishy and subjective, and there's more judgment.
So it's more like qualitative, right?
It can be more qualitative. I mean, you try to make it more quantitative. You think of ways to measure stuff. But I think fundamentally there's a lot of judgment in like, well, you know, this is maybe a good approach. We think this is going to pan out, but we don't really know. We think this technology will work well, but it might not. We might change our minds in 3 months because we share it with some customers and they say, actually, no, that doesn't really work for us. So I think because of that, you know, you have to be a little bit more agile, and it's just a lot harder to plan into the future, frankly. And I think that makes it a different type of management challenge. And you have to build an organization that's a little bit more agile in that way than you would if you were doing something more quantitative and easily measurable.
And so I guess for my last question, this is a very personal inquiry.
Sure.
I was just wondering, this is not a current venture, and this is quite a long time ago, but can you tell us a bit about like what it was like to work on or for Spider-Man 3?
Sure, yeah, that was really fun. Spider-Man 3 was like the last. So I mean, there's so many Spider-Man movies by now. This was Tobey Maguire Spider-Man with Thomas Hayden Church as Sandman.
Yeah.
So my job on that movie was I worked for Sony Pictures Imageworks, which Sony produced it, and then Imageworks is the visual effects division within Sony, where I worked at the time. And so we were doing all the special effects for that movie, and my role was the R&D supervisor for Sand. Sandman, you know, was like this, if you've seen it, is a huge part of the movie, and it was at the time really new. Like no one had ever created a character made out of, you know, a giant pile of sand. And so the question was, how do you make something that on the one hand obeys the laws of physics, looks like sand, moves like sand, but on the other hand, I mean, sand doesn't form into a human, so it can't really obey the laws of physics. So we needed to create this technology that would allow us to ultimately the director, but then artists, you know, working under the direction of the supervisory, the director and the VFX suit and the animation supervisors, to sort of direct the motion of sand in a way where it could be artistic. Okay, form into a person here, and you know, I don't know, what are some of the giant sand monster at some point, and there's a few giant sand monsters, all these kinds of things. But at the same time, it always kind of looked real, physics, you know, obeyed the laws of physics, and so it was a very fun. And so so my job was I basically supervised like the software development and the development of the technology that enabled these artists. We wrote a lot of software, and then we had a team of artists who used that software. And it was very fun because it really combined math and science, math and physics and science and art. Sorry, math, physics, and art in an interesting way. Like on the one hand, I learned a lot at the time about granular material flows, and there's all this tons of, you know, people have studied the physics of sand and dirt and piles of rocks for a long time. It's really important in engineering. If you're like in mining industry has a ton of research in, you know, how does a pile of sand flow through a hopper, right? Or you know, civil engineers that build buildings, they understand, you know, physics of sand. If you sink a pylon into sand, what happens? You know, these sorts. So there's lots of physics and engineering literature. And so it was, on the one hand, learning a lot of that and reading a lot of this, you know, understanding the math and the physics. And on the other hand, you know, you have artists that are like, I want it to look like this. Can I make a pile of sand that does this? And, you know, kind of understanding the math and physics on the one hand, and then understanding the artist's perspective on the other, and kind of conceptualizing how do you bridge the gap, and then give an artist a tool that lets them
do that,
describe artistically what they want, and then somehow does it in a way that sort of, you know, at least qualitatively obeys the laws of physics. It was a very creative challenge. I worked on that project for 2 years with a team of, I think there was maybe eight software engineers I worked with. And it was one of the most fun creative things I've ever done, where I really got to engage the sort of math and science part of me, and also this artistic part of me. And the reward wasn't that, you know, we published a paper and we calculated something. The reward was we had this cool movie where things looked cool. My mom could see the movie and go, oh my God, that looks cool. So that was a very fun, that was a good way. That was the last thing I worked on in the film industry, really, before I moved to NVIDIA. And it was definitely a fun project to end on. Yeah, absolutely.
All right. Well, that was awesome. Thank you so much.
Well, thank you. I had a good time.